Hi, welcome back to my channel. This video is part 3 of Working Stress Design Principle. This is the discussion of Flexure Equation for singly reinforced rectangular beam. Discussion of singly reinforced rectangular beam SRRB, Flexure Equation under Working Stress Design. So before the proper discussion, I just want to give the final answer to the homework number 1. So if you've tried solving them, so you should have solved stress in tension equal to 179.32 and stress in compression equal to 84.21. The rest of the stresses or elastic stresses for A, B, and C of number 2 are as follows. So in here, it's taken that your A is in a cracked section, B and C are cracked section. So please rewatch the video before this. I think that's Introduction to Reinforced Concrete Part 2 if you want to view or if you want to check the answers for the homework. We're given a typical sample of your beam detail wherein we assume and we take your reinforcement at top to be as hanger. It will label B as hanger, meaning there are no stresses at the top members. Only the reinforcement at the bottom are carrying tensile force in which they are subjected to that, and so results to Fs or the stress on your steel. So this would be yielding an equation that we can apply in the analysis of cracked sections, and either we get the nominal moment or the moment capacity, and we can still use the equations later on for us to get the stresses in compression and stresses in tension. So this is the effective depth measured from the centroid of your bars and then at the tip of your concrete at the top. So this would be labeled as your stirrups, and the total area of your reinforcement would be AS. The concrete cover usually for beams is should not be less than 40. So it can be checked on 420.6.1.3 of the latest NSCP. So you can see there your beams, your girders, your columns, which uses also 40, your slabs or walls using at least 20 millimeters, and footings or foundations at 75. We draw your neutral axis in order for us to establish and draw the transformed section for a crack section. As we all know, there will be concrete at the top and then reinforcement at the bottom, and we convert that reinforcement by multiplying it to the modular ratio N. NAS would now be the area of my steel at the bottom of the neutral axis. In this is the crack section wherein we are analyzing SRRB Flexure Equation under the crack stage. So all of the values could only be applied to concrete that are in a crack stage, meaning their actual moment is greater than the cracking moment or the moment capacity of your concrete area. So we will now label the depth or the value, the depth of your concrete at the top of your neutral axis to be C. Your C is the extreme fiber compression to neutral axis distance. So here what we have is C, which would be labeled or which will be measured from tip to tip. So tip at the top and then tip at the neutral axis. It's very important since we will be using C in relating it to your compression, which would later on be will transcribe in the explanations. So after creating or forming your transformed section, we will then transition to the stress diagram of your material. This would be the stress diagram. On the right side, we have on the top right side, we have we have the compression on concrete. Then on the bottom left part would be tension on your steel. So this is FC, labeled the bottom is Fs over N. The distance between the 2 points, tip to tip, would be your effective depth. In reality, your stress here would be in a form of a volume, or would have a volume equal to the following labels. This is the base, this is your KD. You can actually make or have the ratio of your D over C by introducing the investigation factor K. So C is equal to KD. Taking the volume of this stress diagram, it would have 1/2 base FC, height of KD, and then a width of B. So 1/2 FC KD B. Again, that's the compressive force at your concrete. At the bottom, it would have been your tension. Your tension is equal to AS multiplied by FS. So these are forces having a lever arm of JD. So they are opposite in direction and equal in magnitude, that produces a couple with a lever arm equal to JD. So since this is a triangular shape in this section, the force applies at the centroid of your triangle, which measures KD over 3 from the top and then to the application. Knowing these values would now create understanding on the establishment of your SRRB Flexure Equation under WSD. AS again would be your total area of steel bars. It's equal actually to N multiplied by pi dB quantity squared over 4. dB is the diameter of your main reinforcement or bars. K, as mentioned, is the investigation factor and can be computed by this formula, the square root of 2n rho plus n rho quantity squared minus n rho. N is your modular ratio, rho is your steel to concrete ratio. It is equal to AS over BB. So AS, as mentioned, would be the total area of your reinforcement or steel bars at the bottom. And then BD would be the geometric shape or the geometric parameters of your concrete, which would be the width and the effective depth. J, on the other hand, can now be computed from here. So this is JD, the lever arm of your couple. So J is equal to 1 minus K over 3. If we could analyze, this is the total depth D or effective depth D, and then it's comprised of two things, KD over 3 plus JD. Simplifying the expression D is equal to JD plus KD over 3, we can solve for J. J is equal to 1 minus K over 3. So we'll just remember this, or we'll just use this from time to time. Also, when we take the summation of my forces equal to 0, we can understand or we can apply this C equal to T, wherein compression equal to tension. And if we take notice, if my compression is 1/2 FC KDB and my tension is ASFS, we can actually compute for the depth of the concrete, which is C. That's the extreme fiber distance to compression. So, pwede natin gawin yon pag in-equate natin siya, makakakompute tayo ng C. Ganun yung ginagawa natin para makakompute tayo ng X dun sa crack or uncracked sections. So, this could be a part of your analysis that you could apply. But later, I devised 4 steps in order for us to solve the moment capacity, and there will be an alternate solution wherein we will apply C is equal to T. Z is equal to T is compression equals to tension, meaning these are forces of equal magnitude again as opposite in direction. Your moment can be computed by multiplying your force to its lever arm, C, JD, and your T, JD. Therefore, under compression, or on the concrete, moment or maximum moment when concrete stress is at allowable value would be 1/2 FC KJB D squared. Sorry for the bad word, but I can remember this as this one. 1/2 fact Justin Bieber D squared. So if you will forget, you can use that to remember this formula. Also, for tension, maximum moment when still stress is at allowable value would be M equal to ASFS multiplied by JD. As we all know, your 1/2 FC KB or KJ KB D is your compression force, and then ASFS would be your tensile force. So this two would now be can now be used to simply compute the moment capacity, or you can do backtracking of your concrete stress and your steel stress, FC and FS consequently. So this would be the SRRB Flexure Equation under WSD. The next discussion would be working stress design principle, criteria and guidelines, in which we will include the sample problems to apply what we've learned in your Flexure Equation of SRRB. Thank you for watching.